Welcome to this explainer. Today, we're kicking off lesson 1 of our number theory series, where we establish the foundational sandbox of the entire mathematical universe. We're going to define the exact raw materials and the underlying mathematical logic that govern the numbers we use every single day. But consider yourself warned. In this specific mathematical universe, fractions are strictly banned. So if you've ever wondered how simple digits can hide infinite, unbroken patterns, you are absolutely in the right place. Let's get started. Here is our roadmap for the session. First up, the queen of mathematics. 2, the integer sandbox. 3, primes, the DNA of numbers. 4, branches of the kingdom. And 5, the real-world stakes.
Section 1, the queen of mathematics.
Let's dive right into a famous quote from Carl Friedrich Gauss, who is arguably one of the greatest mathematicians in history. He famously declared, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." It's an awe-inspiring statement, right? Number theory is literally one of the oldest branches of pure mathematics, going all the way back thousands of years to ancient Mesopotamian and Egyptian civilizations. Some of the greatest minds in human history, people like Euclid, Fermat, Euler, and obviously Gauss himself, dedicated their entire lives to uncovering the secrets hidden within these numbers. It's not just a branch of math, it is the absolute core of it. Section 2, the integer sandbox. So what are the exact boundaries we'll be playing in? Number theory is primarily devoted to the study of the properties and relationships of integers. In this sandbox, we are entirely isolated to a very specific, discrete mathematical universe. We are dealing exclusively with the set of integers, which mathematicians denote with a capital letter Z. This includes our natural counting numbers like 1, 2, and 3, the number 0, and all the negative whole numbers. You know, the real world we often measure is continuous. It allows for decimals, fractions, and values that just seamlessly blend into one another. But our integer sandbox is fundamentally discrete. There is absolutely no integer between 0 and 1. We have established a strict no fractions allowed rule. They are the uninvited guests we turn away at the door. Now, it might seem simple, but this discrete nature creates an axiom of closure. When you add or multiply integers, you always get another integer. But the second you try to divide them, well, you risk breaking right out of our universe. Managing that division is where the true art of number theory begins. Section 3, primes, the DNA of numbers. Since we're restricted entirely to whole integers, we need to figure out what these numbers are actually made of. Every natural number strictly greater than 1 falls into one of two categories, prime or composite. A prime number is incredibly rigid. It can only be evenly divided by exactly two numbers, 1 and itself. Think of 2, 3, 5, or 7. Composite numbers, on the other hand, can be broken down. Take the number 20, for example. It has divisors other than 1 in itself, like 2, 4, 5, and 10. And when we look closely at those divisors, the ones that happen to be prime numbers, in this case 2 and 5, are called its prime factors. And that brings us to the absolute most important rule of the game, the fundamental theorem of arithmetic. It states that every single integer greater than 1 can be uniquely written as a product of primes. It's the ultimate rule, proving that primes are the unique, inescapable foundation of all whole numbers. You can think of literally any massive number, and it will always have one and only one specific combination of prime numbers that multiply together to create it, ignoring the order they are written in, of course. Just like this quote highlights, prime numbers really are the multiplicative building blocks of natural numbers. Think of it like this. Just as living organisms have a unique sequence of DNA, every single integer has a unique prime factorization sequence. The primes are the elemental atoms. You just cannot break them down any further within our integer sandbox. Now, mathematicians didn't just guess this was true. They proved such a bold claim with incredible rigor. Gauss's landmark book, Disquisitiones Arithmetica, contained the first formal proof of this theorem's uniqueness. To mathematically guarantee that every number can be factored into primes, they rely on powerful logic tools like the well-ordering principle, which basically states any non-empty set of positive integers must have an absolute smallest element, and strong induction. It's this thrilling domino effect of mathematical logic ensuring that no matter how infinitely large numbers get, the rules of their prime DNA never, ever break. Let's make this totally concrete by visualizing these shared prime building blocks using Venn diagrams. When we break down 36 into its prime DNA, it's made of 2, 2, 3, and 3. The number 90 is 2, 3, 3, and 5. Do you notice that overlap right in the middle? They share a 2 and 2 3s. This overlapping DNA is essentially a sneak peek into our upcoming modules where we'll explore the greatest common divisor and the least common multiple. Finding exactly how the prime factors of two different integers interact is a foundational puzzle in number theory. Section 4. Branches of the Kingdom. While the premise of studying whole numbers might sound simple, number theory actually explodes into highly specialized subdivisions. We have elementary number theory, which uses basic arithmetic and induction, but when problems get harder, mathematicians have to borrow some heavy-duty tools. Analytic number theory uses complex calculus and infinite series to understand the density of primes. Algebraic number theory uses rings and fields to measure when unique factorization completely fails. Geometric number theory embeds integers into multidimensional spaces called lattices, and computational number theory uses modern algorithms to crunch massive numbers. They're all just different lenses used to view the exact same integer sandbox. You might be wondering, why do we even need all these complex branches if primes are just basic building blocks? Well, it's because their placement on the number line is wildly unpredictable. If you actually map integers out in a square spiral, a visualization known as the Ulam spiral, you suddenly see these unexpected diagonal patterns of primes emerge. It hints that there is a deeply hidden structure to where primes appear, a conditional independence tied to certain polynomials. All of those complex branches of number theory we just discussed are ultimately trying to tame and predict this beautiful, highly irregular chaos of prime distribution. Section 5. Real-world stakes. Now, let's step out of the theoretical for a minute. Why does this abstract math matter to you personally? What started 2,000 years ago as just a way to manage commerce and accounting in ancient civilizations has evolved into the absolute bedrock of our global digital infrastructure. The properties of integers aren't just academic puzzles, they're the gears running modern society. Literally, everything from secure communications to your daily online banking relies heavily on number theory. For example, public key cryptographic setups use principles directly from elementary number theory. The security of these systems relies entirely on the fact that, while it's super easy to multiply two massive prime numbers together, it is incredibly difficult and time-consuming for a computer to take that massive result and factor it back into its original primes. Furthermore, as we look to the future, geometric number theory and multidimensional lattices are actively being used right now to design post-quantum crypto systems, methods robust enough to protect our data even against future quantum computers. So, as we wrap up Lesson 1 of this explainer, I want to leave you with a final, provocative thought. What happens when the infinite, hidden patterns inside simple whole numbers are weaponized to lock away our deepest digital secrets? The simple integer sandbox we've defined today is literally the battleground for the future of information security. Understanding how these prime numbers interact isn't just about math, it's about understanding the very fabric of digital trust. Keep this in the back of your mind as we move forward in our series, where we'll dive much deeper into the incredible mechanics of division and remainders. Thanks so much for joining, and keep exploring the patterns.